Welcome back. I'm Tutor Wizard Adrian. Please subscribe right here, hit the notification bell. What we're doing is Linear Algebra 1, Chapter 1 is Systems of Linear Equations. 1.8 is Homogeneous Linear Systems, and we're going to do a recap of that. This lecture, essentially, I just said it, we're going to do a quick overview or recap of finding non-trivial solutions to homogeneous linear systems of equations. Let's do that. All right, homogeneous linear systems. This is what it looks like. We mean homogeneous. First of all, we let all the right-hand side b's equal 0. That's what we mean by homogeneous. This is what the augmented matrix will look like. Yes, for simplicity, if you want, those will never change. And so if you keep in mind the fact that we have the equals 0 the whole time, you don't even have to write that in the augmented matrix this time because the zeros will never change. At first, I like to keep it. It's easy. They never change. Write the zeros down. The first thing we point out is that the trivial solution, unfortunately, that's what they call it. There's a whole bunch of terminology, but trivial means 0. So the 0 solution is always a solution to a homogeneous system. Because if I put 0 into this equation all the way along, I will get 0. And if I put it in here, I'll get 0. And if I put it in here, it's 0. So it solves them all simultaneously. The trivial solution is always a solution. Therefore, what we're interested in, and in a lot of, if you watch the previous video on homogeneous linear systems, we solve a couple equations where they come from the real world, where like chemistry and doing combustion of methane in excess oxygen. Then all of a sudden in a real world scenario, we get a linear system somehow. Watch the video and you'll see where we get this homogeneous system. Once we have that, we're interested in not balancing the equation with a bunch of zeros. That is always clearly true. That will work, but it doesn't give us much. What we want is if and when we have non-trivial solutions. We would like a necessary and sufficient condition, and if and only if is the way we phrase this. We don't have this necessarily. I could phrase it this way, but it's a little much at first. What we do have is a good sufficient condition for non-trivial solutions. It's not necessary though. I'll do this. I know now you're starting to talk logic, necessary and sufficient. It's sufficient. What that means is if n is larger than m, remember I put it in brackets, if we have more variables than the equations were listed, so we have 3 unknown variables say, but we only have 2 equations, that always guarantees we have infinitely many solutions or non-trivial solutions. It's not necessary though, because if we reverse that and do the converse, that would say if S has non-trivial solutions, then n is larger than m. And that's not always true. We could have that these are equal, but when we row reduce, one of the rows disappears, and then we will still have non-trivial solutions, even though we started off with n equaling m and not being strictly larger to start off with. So it's not necessary, but it is sufficient. As to finish this off, I'll do an example, and I'll try to explain what necessary and sufficient means, what that theorem is telling us. The theorem, again, is this statement. The sufficient conditions is the way that mathematicians phrase it. We're doing videos, they're just destroying the drums. 2 mini cats playing drums over there. Sufficient conditions. If n is larger than m, then we do always have non-trivial solutions. And that's the way we say it. It's sufficient that n is larger than m will always guarantee that we have non-trivial solutions. But the converse of that statement is false. It's not necessary. What that means is, if you have non-trivial solutions in your homogeneous system, that doesn't mean that n was strictly larger than m. This is the counterexample to that, specifically the converse being false. N is equal to 3, which is equal to m, but when we solve this, we have a row of zeros and therefore non-trivial solutions. So it's not the case that just because we had non-trivial solutions means that n was larger than m. That's not true. The way you're using it is, if this is that, then you're always going to guarantee non-trivial solutions. This is what they're talking about, our third example. Our third example is saying, I have 3 unknown variables and I only have 2 equations. I know before I even start I have infinitely many solutions or non-trivial solutions, specifically augmenting the matrix and row reducing it. There you get REF, and then I can tell the fact that we actually have a secret row of zeros already there. That tells us x3 will be free. I solve for the other ones and I do have non-trivial solutions. That's what the theorem is saying. If you get this where you have n is larger than m before you start, I knew the conclusion to the fact that you can't have a contradiction, you can't have just one solution, you must have infinitely many, which is the only other choice. This is what we're talking about, necessary and sufficient conditions for having non-trivial solutions for homogeneous linear systems of equations. Please subscribe right here and hit the notification bell. I'll see you in the next chapter.